We have a parallel plate capacitor. Each plate has a square shape with side equal to 18 centimeters. The two plates are separated by a distance of 3.2 millimeters, and the capacitor is connected to a battery of 15 volts. First, we'd like to calculate the capacitance of this capacitor. Now remember, capacitance depends on the geometry of the capacitor, so we're going to use the formula related to the geometry of the capacitor. Here's our formula. Capacitance is equal to epsilon 0 times the plate area divided by the plate separation. Let's substitute the numerical values and calculate. We get 8.96 times 10 to negative 11th farad, or 89.6 picofarad. Next, let's calculate the charge accumulated on this capacitor when it's connected to the 15-volt battery. Charge is equal to capacitance multiplied by voltage. So Q equals C times V. When we substitute the numerical values and calculate, we get Q equals 1.34 times 10 to negative 9 coulomb, or 1.34 nanocoulomb. Now let's calculate the magnitude of the electric field between the plates. Electric field magnitude is equal to the potential difference V divided by the plate separation. This is true for a parallel plate setup. The electric field in between the parallel plates will be uniform, and it's going to be equal to potential difference divided by the distance between the two plates. So let's go ahead and calculate the numerical value. And here's the final result. The electric field magnitude in between the plates is equal to 4.7 times 10 to the third volt per meter. Next, we'd like to calculate the potential energy stored in this capacitor. And here's the potential energy formula. U equals 1/2 CV squared. Let's go ahead and plug in the numbers. We get a value of 1.0 times 10 to negative 8 joule, or it's about 10 nanojoule of potential energy. Now, what happens if we disconnect the battery? So let's say we remove this battery and then pull apart the plate so that the plate separation increases to 6.5 millimeters. What happens to all these quantities that we calculated? Now, keep in mind that if we disconnect the battery first and then pull out and then increase the separation of the plates, then one quantity that remains the same is the charge on the plates. Because we have already disconnected the battery, the plates are no longer able to pull any extra charge or push any extra charge to the battery, so the total charge on the plates will remain the same. With that in mind, let's take a look at each quantity again. Does the capacitance change? Yes. Why is that? Because capacitance depends on the plate separation. So let's recalculate and see what the new value is equal to. Here I have recalculated the capacitance value with the new plate separation, and I get 4.41 times 10 to negative 11th farad. How about the total charge? As we have already explained, the total charge on the plates will not change, so it's still equal to 1.34 times 10 to negative 9 coulomb. Does the electric field change? Let's think carefully. This is the formula that we used earlier to calculate the electric field magnitude. It's potential difference divided by plate separation. Now you may think because the plate separation is changing, the electric field must be changing as well. But V is not staying the same either. So why is that? Here's the explanation. Remember, capacitance formula, this is the definition of capacitance, is equal to Q divided by V, right? In this problem, Q is remaining the same and C is changing, so V has to change so that the ratio Q divided by V is now a different value. So D is changing, but V is also changing. It's not that easy to see things from this formula. It's not clear if electric field is changing or not. So you can actually calculate how voltage is changing by using this connection and then recalculate the electric field. But here's a faster way to answer this question. Now, we said that the total charge Q is not changing, right? So this is not changing, but that's what determines the surface charge density sigma on each plate. And remember, in a parallel plate capacitor, the electric field depends on sigma. So it's basically equal to sigma divided by epsilon 0, and it's uniform everywhere in between the plates. Because the surface charge density is not changing, the electric field magnitude is not going to change. So both V and D will change. They will both increase such that the ratio electric field magnitude remains the same. And again, how do I know that the electric field magnitude has to remain the same? That's because the surface charge density on each plate is staying the same. So to summarize, because Q remains the same, sigma remains the same, therefore E, the electric field magnitude, does not change. Still equal to 4.7 times 10 to the third volts per meter. How about the potential energy? Earlier in this problem, we used this formula, potential energy equals 1/2 CV squared. Should we use it again to recalculate the potential energy? We could, but again, we would have to recalculate the voltage first because it has changed and we don't know the new value. We do know the new value for capacitance. We already calculated that. So let's actually use an alternative formula for U, which is right here. So we can directly use U equals Q squared divided by 2 times C. Now you may be asking, where does this formula come from? Well, it's just a combination of this original formula and the definition of capacitance, C equals Q divided by V. So nothing magic here, nothing new. We can just use this shortcut formula to recalculate the potential energy. And why is this more convenient? Again, because I know that Q has not changed. C has changed, however, I know the new value, so I'll just go ahead and plug in the values and calculate quickly. What we get when we recalculate the potential energy stored in the capacitor, it's equal to 2.04 times 10 to the negative 8 joule. Now this is about twice as much as the previous value that we calculated, so the potential energy stored in the capacitor has increased. Now, where does this energy come from? Well, this comes from the person who's actually pulling the plates apart. So by increasing the plate separation, we do work on the system, and as a result, the system gains potential energy.